Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is another video in a series on antiderivatives, and this one specifically, we're going to talk about how to approximate areas underneath curves. Now, if you happen to know the punchline to all of this, don't let anybody else know. Because the reality is, it's much better to learn by surprise, I think, because it's more impactful. So let's go ahead and just investigate a very kind of easy way, or a no-nonsense way of approximating the area, in quotes, under a curve. First of all, I want to really be clear about this. When somebody says the area under a curve, really what they truly mean is the area between the curve and the x-axis. So if your professor says something like, I need you to compute the area underneath, let's say, the sine curve, since I've just drawn that out, from 0 to 2 pi, you should think of it this way. There's a positive area here between the function sine of x and the x-axis, and then there's a negative area right here between, again, the function and the x-axis. Again, this is a positive area and that's a negative area, and actually those areas will cancel each other out. So if somebody said, I need to know what's the area underneath the sine curve, y equals sine of x, and I need you to figure out that area from, let's say, 0 to 2 pi, you could easily just say the area would be 0 because the upper half would cancel with the lower half. So in this conversation and in calculus, areas are allowed to be negative, even though technically speaking, that's actually impossible for an area to be negative. Mathematically, they are allowed to be negative for our discussion purposes. As we move forward, we will let go of the area concept and then really just focus on signed areas, this plus area and the negative area right there. So this whole talk is kind of with that statement in mind, that areas can be negative and they can cancel out positive areas. All right, that all being said, let's go ahead and just erase that and get into the nitty-gritty of what we're here for. So the graph that I've handed you here, I want to really use this graph to ask this question. What does the area underneath this curve specifically, what does the area underneath this curve represent? If you think of the units for the vertical axis, it's in meters per second. That's what that s to the negative first really means. It's very bad formatting, but it's meters per second. So meters per second. That's velocity in meters per second. And the horizontal axis is in seconds. So if I were to look at just a small portion, and actually there's a highlighted portion right there, and I'll go ahead and highlight it, this area right here. If I wanted to know what is, I don't really need to know what that area actually is, but I would like to know what does it represent. Well, if you think about an area, it's width times height here. So think about this, it's just its width times its height. And of course, we could approximate that, right? This area of this block is 1, and let me use a different ink so you can really see. That area is 1. This area is approximately 1. It's not exactly 1, but it's approximately. And we can further say that maybe this area up here is approximately a half. And we could say this area right here is approximately 3/4. And I'll just bleed this area into that approximately a half, since it's really kind of less than a half. So if you wanted to know what numerically what this area is approximately, you say it's roughly about 1 plus 1 plus a half plus 3/4, which would be 3 and a quarter. Okay, so that area is roughly 3 1/4, but nobody's really asking that. What I'm really truthfully asking here is, what is that area? What does it represent? Well, the way you can do that is just take its width, the units for the width, which are in seconds, and multiply those by the units for the height, which are in meters per second. And that area right there would represent the number of meters, because that's what meters per second times seconds gives you, a certain number of meters. What does it mean, a certain number of meters? Well, they have times here, so times 7 seconds to 9 seconds. So it's the distance that whatever we're talking about, maybe it's a bike, maybe it's something else, somebody running, whatever it is, it's the distance covered in that many seconds. So the number of meters covered or traveled in that time period, traveled. And in this case, we know that between 7 and 9 seconds, this object, whatever we're talking about, has traveled roughly 3.25 meters, because again, we just approximated those areas, and the area is representative of the number of meters covered by this object. This is kind of the basis of what we're going to be doing, not only in this series of videos, but actually all throughout the rest of calculus. You're basically looking at these areas underneath these curves and trying to approximate their values and maybe even interpret what they mean. The big question is, how do you approximate those areas? And we're going to develop that method here, and then we're going to codify that method in the next video. So right now, let's go ahead and consider the function f of x, which is equal to x times the cosine of x plus 2. And we're just going to consider that on the interval from 1 to 2. And just to let you know, I have a Desmos application. Well, it's not an application. I have a Desmos a page dedicated to this, and that is the address. You're more than welcome to go to it. It's not going to break my Desmos. And that's going to help us really visualize what this graph looks like. And actually, as I was just about to go there, I realized this is an older version of it. So I'm just going to cross this out here, and I'm going to give you a new address here. I think what happened was I made a modification to it and it saved as a completely different URL. Not that big of a deal. Anyway, we want to look at this function just from x equals 1 to x equals 2. And I'm going to graph this by hand first so that you can see this problem without us touching technology and we can talk about it. Just to let you know, I am not graphing this by hand using some type of magical skill, like I know exactly what this curve looks like before, or that I would know what this curve looks like if anybody handed it to me or something like that. No, I happen to be looking at the curve off to my right. So the x times the cosine of x plus 2 is not something I would memorize. Okay. All right. That being said, let's go ahead and take a look at this. And I went ahead and changed the color of the roof on that so that we can have a pretty good conversation and use different colors for other things. So I've turned off this, and part A says use 4 equally spaced rectangles to approximate the area underneath this curve using left endpoints. That's going to require a little bit of conversation here. So when I say left endpoints, let's ignore that for the moment and let's just talk about 4 equally spaced rectangles. You get those 4 equally spaced rectangles by breaking this into 4 equally spaced regions. Now that's going to be kind of difficult because I didn't actually measure this out or anything like that. So I will just pretend as though the 4 equally spaced regions look like this. And I'm going to use, I'll use blue to break it up. So 4 regions means I go halfway, halfway, and halfway. And you should probably agree here that this is actually 4 equally spaced slices. I'm just going to go ahead and draw the slices in here. And this idea of slicing like this is going to be with you for the rest of calculus. So you might as well just get used to it. You're slicing intervals up into what we call n subintervals. In this case, 4 subintervals. So hopefully you see it's not actually equally spaced, but let's pretend that they are. All right, because I'm freehanding this for the most part. So we have 4 sort of rectangles, but we actually haven't drawn a rectangle in. You know what? That's going to bother me that they're not equally spaced. All right, there. Now they're evenly spaced. Okay, so we've divided this into 4 evenly spaced intervals. One thing I do want to note here If they're equally spaced intervals, then the step size to each of these intervals must be the same. That is, this distance right here has to be the same no matter what. And computing that distance is a kind of a no-brainer, but I'm just going to go ahead and introduce a little bit of notation here. We're going to say that distance is a little wiggle in x, a small little wiggle in x there. And that will just be the entire interval here diced into 4 pieces. So that entire interval is actually the distance between 2 and 1, which is a distance of 1, and we're dicing it into 4 intervals. That is, each little sub-interval has a width of 1/4. So let me go ahead and just mark that down here. This has a width of 1/4. This has a width of 1/4. That has a width of 1/4, and so does that. I feel like Oprah. All right, so let's go ahead and now talk about how we're going to place rectangles in here. Because right now, these are just divided up. Like a loaf of bread, you've just done a bunch of slices here, right? But they say, they being me, use 4 equally spaced rectangles to approximate the area. Rectangles. Well, those are not rectangles. They're more like trapezoids in a way, but they're not rectangles. So, how are we going to build our rectangles? Well, they say use the left endpoints. What does that mean? It means in each sub-interval here, I'm going to use the height at the left endpoint to determine the height of the rectangle. And because I want to use this for future computations, I'm going to go ahead and copy this so that I can use it later on. So I've copied that. Now I'm just off to the races. So here we go. In this first slice, this one right here, we're going to use its left endpoint, the function value at its left endpoint, to build a top on this rectangle. So I'll just go ahead and put a top on here, and note, I don't need a ruler for this piece right here. I can zoom in and cap it off. So this is we're going to approximate the area underneath that slice using that little rectangle. We use rectangles because, well, it's easy to compute an area using a rectangle. It's just width times height. Then we move over to the next slice and use its left endpoint to put a cap on that slice. Having a moment there, not being able to draw that in. And let me just go down here, and we'll go ahead and highlight that slice as well. And just to make it sort of different than the other one, I'm going to use a different color because I want to, and it seems as though my pen is just the right size for that. And then the next slice will do the left endpoint, and so on and so forth. And when you're done, you have these colorful little rectangles, but you also can easily compute the area, or an approximation of the area underneath this curve, by summing up the areas of all those rectangles. Notice that you will have to find the function values, at each of those edge points. Sorry about that. That was not supposed to be a highlighter. In fact, it was supposed to be the yellow highlighter anyway. So I'll say the area is approximately equal to, and we use L sub 4 to tell the world that we've sliced this curve between 0 and 1, or sorry, 1 and 2. We've sliced that curve into 4 slices, and we've used left endpoints. That's what L sub 4 means. I've sliced that area underneath that curve to the x-axis into 4 subintervals equally spaced, and we're using the left endpoints to approximate the heights. So for the first subinterval, it's going to be, I want black ink, please. The first subinterval will have a width of 1/4, and its height is going to be f evaluated at 1. The second subinterval will have a width of 1/4, and its height will again be the function evaluated now not at 1, but at 1 plus 1/4. So I'm going to write that in here. That point right there is 1 plus 1/4, or 1.25. And in fact, this one is another quarter away, and this one is yet another quarter away. So that gives us all of our points that we're going to evaluate at. So this is 1.25. And then plus the what is that? I don't know, puce. I have no idea what that color is. But anyhow, that color has a width of 1/4. And the function height at the left edge there is based upon f of 1.5. And then the function height at the next slice, the orange slice, well, that function height is f of 1.75. Notice we have 4 slices and we have 4 little approximations there. And now I just go to the function itself and I can plug in those values. Of course, this is not going to be pretty because we're dealing with a cosine, but at least I can factor out the 1/4 and I'll be left with plug 1 into the function. You have 1 times the cosine of 1 plus 2 plus now we plug in 1.25 into the function, so plus 1.25 times the cosine of 1.25, again plus 2, and then we move on to the next one. Yeah, remember I already factored out the 1/4, so then 1.5 cosine of 1.5 plus 2, and finally the last one right here, plus 1.75 cosine of 1.75, again plus 2. Note, in calculus, you should be working in radians. So once you grab a calculator, you want to make sure you're in radian mode. Obviously, this is going to require a calculator to approximate. So I'm just going to grab my calculator here. And we get approximately 2.18. That would be the approximate area underneath this curve from 1 to 2. Now, there are a few things I need to mention here. 1, using the left endpoints was just a choice in this problem. Of course, we could have used the right endpoints, so we are going to do this problem again using right endpoints, but I just wanted to make that very clear that using the left endpoints was a demand by me, but when we move forward, eventually we'll be able to make our own decisions on how, which edge we want to use. Second thing I want to mention, this is an over approximation of the area. Notice all of our rectangles there, the areas sum up to an area that's greater than the area actually between the curve and the x-axis. If I just kind of scratch out the area between the curve and the x-axis, that's what it is right there, all this stuff. Notice what we have shaded though is greater than that. So that's just a thing to note. And we'll have that in a theorem later on, that when you have a decreasing function and you use left endpoint method, which is what this method is called, you will have an over approximation of your area. If you use a right endpoint method, again on a decreasing function, you will have an under approximation of your area. Well, such is life. So let's do the same thing, but this time we're going to go ahead and use the right endpoints. I'll paste in that curve, beautifully done. And now we'll go ahead and use the right endpoints like I just said. Let me just showcase kind of slowly here. Actually, I don't really have to do very much because it's kind of easy to do the right endpoints. These, in the first interval, this is the right endpoint. So I'll have that as my cap. And this is the next right endpoint for the second interval. Third subinterval has that as its right edge point. Again, the right endpoint means the function value at the right endpoint. So in this last interval, the function value on the right edge is right there. And so we put a little topper on that. And now I'll just highlight the areas. Whoops, I don't want it that large. I'll highlight the areas so you can see what we're gonna sum up. And you can also see, once I'm done here, that this is definitely going to be an underestimation or an underestimate of the actual area underneath that curve. Remember, left endpoints in this case gave us an overestimate. This will give us the underestimate. It's probably helpful to name what all of those x values are. So remember the step size, because we cut things into 4 pieces and this interval is of length 1, the step size is 1/4. And so this point is 1 1/4. This point right here is 1 1/2. And this point is 1 3/4. Now I'd like to sum up all of those areas. The height here is going to be f evaluated at 1 1/4. The height here is going to be f evaluated at 1.5. the height there is the function evaluated at 1.75, and finally, the height there is the function evaluated at 2. Notice in the last problem, we did not use the very far right edge. We did not look at f of 2 in the last problem. This problem, we're not looking at the very leftmost point. We're not looking at f of 1. So that's just because we're only using right endpoints in this. So the area is approximately right endpoints using 4 slices. That's what this means. The 4 means the number of slices, and the R means you're using right endpoints. It is kind of critical that you let people know what you're doing. And here, the right endpoints using 4, well, notice each of these widths have a quarter in common. So technically, height times width, all the widths will have a 1/4. I could factor that out, and now I'll just have the sum of the heights. So it'll be f of 1.25 plus f at 1.5 plus f at 1.75 plus f at 2. Remember, our function was x cosine of x plus 2. So I'm just going to evaluate that function at these numbers, f of 1.5 and so 1.25, sorry, and 1.5 and so on and so forth, and multiply that result by a quarter. And in this case, after grabbing a calculator, I get roughly 1.84. Now remember, hopping back here, we got a 2.18. Well, that was because we had an over approximation, sorry. In this case, we have a 1.84, which is an under approximation. So the real area is somewhere between, let me just put that in here. The real area is somewhere between that 1.84 and whatever that other one was it 2.18. So I'll just put 2.18 here. So we have a okay estimate for the area underneath that curve, but it's not the best. And by the way, my part C, if you're one of my students and you have the printouts of these lectures, obviously I've kind of already said the answer to this. The first one, the left endpoint method, is an overestimate of the actual area. The right endpoint method, in this case, is an underestimate. Now I want to go to that Desmos webpage where I have everything saved because I want to show something to you. So here we are in my Desmos here. This is the app that I had kind of coded in. You could change the function if you want, doesn't really matter. A and B just means the interval that you're worried about. I'm going with the interval from 1 to 2, and let me put this in projector mode so it's easier to see. So I'm going to go from 1 to 2 here. Just move that back. Okay. And then let's go ahead and just say we have n is the number of slices, so we have 4 slices. And the rest of this you don't have to worry about. Now I'm going to go ahead and click on left endpoints. And that's what we had there. Now I don't compute the area. What I'm just doing is showcasing a visual of what we just did. That is literally what we just did. If I turn off that folder and turn on the right endpoints, that was the second method that we did. There is a hybrid between left endpoints and right endpoints called midpoints, which we'll talk about a little bit later. It looks confusing, but it's actually a really good method. Obviously, if I go back to the left endpoints and I increase the number of slices, we start getting a better approximation of the actual area underneath the curve. And I stopped this at 20, but I can go all the way up to, let's just say we stop it at 50. Okay. So let me do that. I'm just keep going. And you can see that that's probably a pretty darn good estimate of the area underneath the curve. If I sum up all of those little areas of the rectangles. So this is what you're eventually trying to do, is get a better approximation. And the best way to do that is to let n get very large. The problem is that means that you have to compute a lot of summations. Well, such is life, right? Also in this applet, just letting you know, you could also increase the b value. So here, maybe I'll stop b at 4. So there is a visual of left endpoints, 4 slices from x equals 1 to x equals 4. Notice this little empty slice it looks like. It's because the left endpoint there is hardly negative. It's just barely a negative number. And so it's a very small little slice there. So that's just a heads up that sometimes when you use these methods, you end up seeing these blank areas. It's because you need more slices to actually see that get filled in. And when you put more slices in, there you go. You get this beautiful visual of the area. So that's really the point of this video, is to get you used to what we're going toward in Calc, at the end of Calc 1, at the beginning of Calc 2, and basically all of Calc 2, is areas underneath curves. Now, the basic idea is areas underneath curves. Eventually, we shed that idea because of the fact that areas generally cannot be negative, and so we don't like saying areas underneath curves when they're negative, but such is life. But the other thing I want to mention, the last thing I want to mention in this video, is about that overestimate versus underestimate idea. I want to codify that and have that written cleanly for you. Here's the theorem. If f is increasing on an interval from a to b, I'll draw this out because it's easier to see. So it's increasing on some interval. And if you use right endpoints, so let's say you slice this interval right here from a to b, you slice it into, let's just make our lives a little bit easier and say 4 pieces. So 1, and then 1, and then 1. So you, those are 4 slices. If you use right endpoints, I'll use red for right, you get an overestimate if your function is increasing. And that should make sense. So whereas if you had the same curve, let's go ahead and draw that out, and it's on the same interval, which means I should have honestly copied this, but this is, oh well, such is life. Okay, from A to B, if you use left endpoints as the toppers, you get an underestimate. Again, if your function is increasing. So if f is increasing, then r sub n, the right endpoint method, will be an overestimate, and L sub n, the left endpoint method, will be an underestimate. On the other hand, if you graph out a decreasing function, which is actually what we just had seen, but let's just go ahead and just show it again. So from A to B, this time I'll be smart enough to copy this. So let's slice this into 4 pieces. And just to give you a heads up, we will be doing slices more than 4 slices, very frequently, in fact. But let me move this off to the side. So there's my 2 decreasing functions. If you use left or right endpoints for a decreasing function, use my caps using the right endpoints, you have an underestimate of the area. If you use left endpoints for a decreasing function, you have an overestimate of the area right here. So, and that's what this theorem is saying. If f is decreasing on the interval, then r will be an underestimate and L will be an overestimate. All right. So in the next video, we're going to start going into actually talking about a hugely important topic in all of Calc 2, which is called a Riemann sum.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud.